Welcome to this exploration of the optimization algorithm that became the default choice for deep learning. In 2014, Diederik, Kingma, and Jimmy B.A. published ADAM, a Method for Stochastic Optimization. This paper introduced ADAM, Adaptive Moment Estimation, an optimizer that combined the best ideas from previous methods and added innovations that made it remarkably effective. ADAM powers the training of most modern neural networks. Let's understand why. Training neural networks means finding good parameters. The goal: minimize a loss function by adjusting millions of parameters. The challenge: the loss landscape is complex, high-dimensional, non-convex, noisy. The approach: stochastic gradient descent. Update parameters in the direction that reduces loss. The basic SGD has limitations. Standard SGD. Update rule: that AXG, where G is the gradient and A is the learning rate. Problems: one learning rate for all parameters. Noisy gradients cause oscillation, slow progress in flat regions, and it's sensitive to learning rate choice. Researchers developed improvements: momentum, adaptive learning rates. ADAM combined them. Momentum improved SGD. The idea: accumulate a velocity based on past gradients. Move with momentum. Update: V plus G, AV. Benefits: smooths out noisy gradients, accelerates in consistent directions, and helps escape shallow local minima. Momentum uses first moments of gradients. AdaGrad and RMS-Prop adapted learning rates per parameter. AdaGrad scales learning rate by accumulated squared gradients, meaning parameters with large gradients get smaller learning rates, and those with small gradients get larger learning rates. RMS-Prop uses an exponential moving average of squared gradients, fixing AdaGrad's diminishing learning rate problem and being better for non-stationary problems. These use second moments of gradients. ADAM combines momentum and adaptive learning rates. First moment estimate: V1M plus G. Second moment estimate: VV plus G2. Update: Theta IXM. ADAM adapts learning rates like RMS-Prop while having momentum like momentum. A key insight: initial moments are biased toward zero. The problem: M and V start at zero. Early estimates underestimate true moments. The solution: bias correction, M arc M and V arc V. As T grows, V approaches zero, and correction approaches 1. Early bias is compensated. Initialize: M0, 0, V0, and 0, T 0. For each step, T plus 1, G, loss, M, V plus G, V rear, V2V plus G2, M rear, V rear, V rear, The AXM rear. Default hyperparameters. Appreciate Demystified 1, Buffy 1 Bear 0.9, Letter value for 0.999, mas for 10 to the minus octo. The defaults are carefully chosen. V1 0.9 smooths gradients over about 10 steps, providing enough momentum without being excessive. V2 PAF 0.999 offers long memory for scaling, ensuring stable learning rate adaptation. At 7.01 works for most networks, being neither too large nor too small. A first 10 to the minus 8 prevents division by 0 and rarely needs changing. These defaults work remarkably well across diverse problems. The paper demonstrated ADAM's effectiveness. Logistic regression was faster than SGD and AdaGrad. Multi-layer networks showed competitive or better performance than RMS-Prop. Convolutional networks achieve strong performance on MNIST and KIFAR. Adam was also the recommended optimizer for variational autoencoders. Adam was consistently among the best performers. The paper provided analysis. Adam achieves O regret for convex functions, and under certain conditions, Adam converges. Its adaptive step sizes effectively adapt to gradient geometry. Later work found issues with the convergence proof, leading to variants like AM-SCRAD. Adam became the default because it requires minimal tuning, as default hyperparameters work well. It offers fast convergence, often quicker than alternatives. It is robust, working across various architectures and tasks. It's easy to implement, requiring just a few lines of code, and it's memory efficient, storing only 2 running averages per parameter. A long-running debate exists between Adam and SGD. Adam's advantages include faster initial convergence and less sensitivity to learning rate, making it work out of the box. SGD advantages are often better final generalization, simpler dynamics, and it's preferred for some vision tasks. In practice, use Adam for quick experiments. Consider SGD for final training. Researchers noticed a pattern. Adam trains faster, but sometimes generalizes worse than SGD. The hypothesis is that Adam converges to sharper minima, while SGD finds flatter minima that generalize better. Solutions include Adam W and reducing the learning rate late in training. This sparked research into optimizer generalization relationships. A crucial refinement in 2017 was Adam W. The issue was that standard Adam combines weight decay with adaptive gradients incorrectly. Adam W decouples weight decay from gradient adaptation with the update Thi Si Har Thi AXM As L X Thi. This had a significant impact, leading to better generalization and becoming standard for transformers like BERT and GPT. Many variants address specific issues. AMS-GRAD fixed convergence proof issues. RADAM or rectified Adam provided automatic warm-up. Ada belief adapted to gradient confidence. Look-ahead combined with any optimizer for stability. LAM was developed for large batch training. Each variant has use cases, but Adam remain most common. Adam trains diverse systems. In computer vision, it's used for AlexNet descendants and ResNets. For natural language, it powers BERT, GPT, and LLMs. In reinforcement learning, it's crucial for DQN and its variants. It's also vital for generative models like VAEs, GANs, and diffusion models, and in science, for applications like AlphaFold and protein prediction. When in doubt, start with Adam. Intuitions for Adam's success. Normalization, dividing by V, normalizes gradient scale across parameters. Momentum smooths noisy gradients and accelerates progress. Adaptation means each parameter gets its own effective learning rate. Robustness ensures it works even when hyperparameters aren't perfectly tuned. The combination handles many pathologies of lost landscapes. Diederik Kingma also invented the VAE and made major contributions to generative models. He is now at Google. Jimmy B.A. is an influential researcher on optimization and neural networks, and is now a professor at the University of Toronto. Their work on both Adam and VAEs shaped modern deep learning. Adam is among the most cited machine learning papers, with over 150,000 citations. Every deep learning framework includes Adam, and it's the default choice recommended in tutorials, courses, and research. Its practical impact is immense, having trained countless models. Adam teaches important lessons. Combine ideas, as Adam merged momentum and adaptive learning rates. Bias correction matters. Showing small details can have big effects. Defaults should work, enabling broader adoption. Theory guides practice, as understanding moments motivated the design. And keep iterating, as variants like Adam W improve the original. Practical guidelines for using Adam effectively. Start with defaults. A00 had the 01, V1 0.9, V2 on 0.9999. Use Adam W for transformers for better generalization with weight decay. Try learning rate schedules like warm-up or cosine decay, as they often help. Consider SGD for vision, as it may generalize better for CNNs. And always monitor training, ensuring loss decreases smoothly. Adam's journey began in 2014 with the original paper at an ICLR workshop, followed by wide adoption in 2015 after formal publication. In 2017, Adam W. addressed weight decay issues. From 2018 to 2019, it powered BERT and GPT-2 training, and from 2020 onwards, it remains the default for most deep learning. Optimizers have continued to evolve, but Adam remains central. Adam, a method for stochastic optimization, introduced the optimizer that trained the AI revolution. Kingma and Ba combined momentum with adaptive learning rates, added bias correction, and produced an algorithm that works remarkably well across diverse tasks and architectures. Adam's gift is reliability. With minimal tuning, it trains neural networks effectively. This enabled researchers and practitioners to focus on architecture and data rather than optimization minutiae. Every time a neural network trains, whether it's recognizing images, understanding language, or generating art, it's probably using Adam or a close variant. The algorithm is elegant. Accumulate gradient moments, correct for bias, adapt learning rates. The impact is enormous, enabling the training of systems that are transforming technology and society.